Hello, so in this video, in this final part of this chapter about constant acceleration, about things moving, we're going to look at things moving, particularly when they're going to be falling down, okay? So this picture, for example, we've got this tennis ball. Originally, this person is holding the tennis ball, then it releases it from its hand, right? And the tennis ball moves down to then hit the floor, right? And what we'll be doing then, actually what we looked at so far is using SUVAT, right? So the displacement, the velocity, the acceleration, the time. We can apply SUVAT to now situations where things are falling down, okay? And what's particularly interesting with this is if you have anything falling down, so if I draw again something, so let's say again I have something falling down, right? This little ball that's falling down to the floor, again a floor here. What's so interesting is, particularly when we say the only thing that's pulling this ball down or this object downwards is its weight, right? Kind of like its gravity, right? That's pulling it down. If there's no air resistance or anything like that, no other forces other than purely the thing pulling it down, right? What it turns out is the acceleration, right? So the acceleration tells me again if it's speeding up or slowing down. It turns out the acceleration is constant. Hence, because it's constant, we can apply what we've done so far. And we can apply the formulas, right? The SUVAT formulas to this situation. And it turns out in particular the acceleration when things fall down in this way, the acceleration because of gravity, right? The acceleration due to gravity is this letter G, okay? This letter G, and it turns out it's the actual acceleration when things are falling down is 9.80665 meters per second, okay? So this number here, it's been found out that the acceleration because of gravity, so when things move down, they fall down. The acceleration in this case is this number here. Obviously, this is we don't use this whole number. What we would do is we'll sort of round it, right, to approximate. So what we say in this course in particular, what we'll be using, if you're not told what value of G, this gravity acceleration number, what to use, we say that G is by default 9.8, okay? So we use it to one decimal place, okay? So what we'll be saying is the acceleration when things move down will always be 9.8, regardless if it's a feather or a heavy brick of metal. No matter how light or heavy a mass is, it will always accelerate downwards at the same amount, okay? Always 9.8, okay? With what we'll be using in this course. So no air resistance, purely just moving down. So the acceleration will always be 9.8, okay? That's on Earth, however, okay? If you're on the moon, obviously if you're on the moon, obviously you just jump everywhere and you just barely fall down. There's like no actual gravity, right, to bring you down. So the acceleration, the gravity acceleration will be different. So on every different planet, the accelerations will be this gravity acceleration, right? The acceleration due to gravity will be different on every planet. But every question will be based on Earth, right? So on Earth it's 9.8, and that's what we'll be using on this course, okay? So that's the main premise. So with this acceleration number, we can use SUVAT to consider things moving downwards, okay? Right, and so what will happen is, again, for example, like a tennis ball, obviously things will perhaps obviously be in the air, and then they'll come down, okay? And they'll come down, and then they'll hit the floor, okay? Now, the other thing we're going to consider, we're going to look at some examples. The other idea we're going to consider in this section is, what about when things bounce up, okay? So obviously, let's say this tennis ball moves down and then it hits the floor, right? But then what about when the ball is shooting upwards, okay? Because things can move up, okay? So they bounce back up. Obviously, if they bounce back up, the tennis ball's going to go up and up and up, but then it's going to slow down, right? It's going to slow down, and eventually it will basically be in the air, then it'll come back down. Okay, so the idea is, obviously, when the ball comes upwards from the floor, or it will go up, then it'll reach this point, this maximum point, and then it'll come back down to the floor. Okay, so obviously things don't go up in the air permanently, right? Like think about like a football or even a tennis ball. If you kick it up, it's going to come back down eventually, right? Anything that comes up will have to come back down eventually, so it reaches a maximum height, right? So that's what we'll be considering, max height, or the maximum distance it moves, okay, upwards. So when that happens, when it moves up and then it can't move up anymore, then it'll come back down. That has to occur when its speed is 0, okay? So the speed would have to be 0 when it reaches the maximum point it can reach, okay? If that makes any sense? Because then it moves upwards and then it has to come back down. Well, in between, the speed has to go to 0, right? Because then it has to come to rest. It has to come to some sort of stop before it then moves back down, okay? So anything to do with maximum height, we need to consider the velocity, the speed, to be 0. So I'm going to say at the maximum height or distance, the speed must go to 0. Okay. Okay, so we will be considering that as well. So the maximum height that things can go up in the air before they come back down. Okay, again, like a football, if you kick it up in the air, it will have to come down. What's the highest point it can go in the air? Right. Right. Okay, so let's have a look at some examples. Okay, so we've got this question then, and again, we will be using our SUVAT formulas. Right, so we're told a book falls off the top shelf on a bookcase. The shelf is 1.4 meters above the wooden floor. Find the time the book takes to reach the floor. So, okay, so let's again sort of draw this scenario. So, okay, it's on the bookshelf. Let's say the bookshelf is here. There's a line here. And so this is the shelf. And then the shelf is 1.4 meters above a floor. So we have the floor, let's say here. Then the distance, right, the height of the shelf has to be 1.4 meters above ground. Okay. And so what's happening is we have this book. I'm just going to draw this little dot here. This book, obviously it goes off the shelf and then it'll come back down and then hits the floor. Okay, that's the idea. So it's falling down. It's in what we call free fall. Okay, it's just moving downwards due to gravity. And so the acceleration in this case will always be, as in every example here, be 9.8 meters per second. Okay, per second. Right. So, with that in mind, they want me to find the time the book takes to reach the floor. Okay, so what time when it starts from the shelf and then it comes back down, what's the time? Okay. So, right. So, firstly, we're going to use our SUVAT again. So, we've got our distance, our displacement technically. So, directions matter. Right, directions matter. So firstly, the displacement, obviously, if it goes from the shelf to the floor, it's travelled 1.4 meters and it's going down by 1.4. The acceleration is also going down. What we can say is we can take the downwards as the positive direction. Okay, so that means when things go down, that makes it positive. So 1.4, because it's moving down by 1.4 meters, that would just be 1.4 displacement. The initial velocity, well, it's from rest, right? It's from rest. It starts from, they're not explicitly told you, but originally it's not really moving, right? But then it moves down due to gravity and that'll make it move downwards, right? So initially it's at 0, there's no speed, but then it will pick up the speed as it moves downwards. So the initial velocity is downwards by 0. So that's 0. The final velocity, so the velocity when it hits the floor, So if I call that v, well, actually, we don't care about that at the moment because we want the time. Then the acceleration, again, it's downwards by 9.8. Cool. And then t, the time is what we want to work out, right? So if we use that here, okay, but which formula does not include v? This one here, right? S is ut plus a half at squared. And at that point, we just use the formula. So 1.4 for S is going to be 0 lots of t, so 0. 0 add a half of 9.8 of t squared. Okay. And so if we solve this then, well, simply 1.4, well, half of 9.8, that's going to be 4.9, so 4.9 t squared. So therefore t squared is 1.4 over 4.9, which is 2 over 7, okay? So therefore t, if we root that, it's going to be root 2 over 7, and I guess as a number, as a decimal, oh, that goes to root 14 over 7, simplified, and that goes to 0.53 seconds to 2 decimal places, okay? So that's the time it takes from when it leaves the shelf to then when it hits the floor. So the time it takes dropping down. Okay, then part B, the speed when the ball strikes the book strikes the floor. So again, obviously it starts from rest and then it hits the floor with some speed v, okay? So when the ball drops down here at the floor, it reaches that with a speed v, right? So what is that speed? Well, okay, so we're going to use that again. But again, S, it's moved down by 1.4 meters. U, the initial velocity is 0. V is what I do care about, the final velocity when it hits the floor. A is 9.8, and T, I actually don't care about T here, but I do have T, but I don't care about it. So again, which formula does not include T here? This one here, V squared is U squared plus 2AS, right? So then V squared is going to be 0 squared, add 2 lots of 9.8 lots of 1.4, and that will be V squared is 27.44. So therefore that means V is going to be the root of that. Which is 7 root 14 over 5, or as a decimal, 5.24 meters per second to 2 decimal places. So that's the speed when it hits the ball, hits the floor, right? Okay, so that's generally the idea with this sort of with what we're looking at, right? Okay. Let's have a look at this question then. So we're told a ball is projected upwards. So now it's the sort of opposite, where instead of falling down, it's been sort of booted upward like a football, right? It's been kicked or moved upwards. So this situation is, let's have a read. So the ball's projected upwards from a point X, but that is 7 meters above ground with speed 21. Okay, so if we draw it again, so again let's have a floor, right? Our floor, and then we have this point X. So this point X here, that is 7 meters above ground. So 7 meters here. Right. So the ball starts here. So again, I'll draw this little dot. So it's 7 meters above ground with speed 21. Now the speed is upwards, right? It's going upwards by 21 meters per second. But there's also acceleration, right? So the acceleration, again, gravity, essentially, it'd be going downwards, okay? It would be pulled downwards with acceleration G, which is 9.8, right? Okay, so it says firstly the greatest height reached by the ball. Okay, so the greatest height. So as we discussed at the start, the ball's obviously going to, if it's been shot up by 21 meters per second, and it's going to want to come down because of gravity, right? It's going to eventually come to a stop in the air, right? It doesn't move. It won't move anymore, so the speed will be 0, right? And then it will come back down. So it will move up, and then it will come back down to the floor. Okay. But what's this height then? What is this height here? And what's the height? Okay. What is the height? So, okay. So again, if we use our suvat, what S? So think about it. We're starting at the point X, which is 7 meters above. So we're starting at X, and then we start from this point to the point here where it comes to rest. I don't know the height. I don't know the distance from the starting point to when it comes to rest here in the air. So that's what I want to work out, right? This sort of height. So the initial speed is 21. V, I know what V is. It has to be 0, right? If it comes to rest, right? If it stops moving forwards and then comes back down, it'd be 0. The acceleration is 9.8. But because the ball is moving upwards, it's against gravity, so it's moving, so the velocity is upwards, right? It's moving up, but the acceleration is going down. It's in the opposite direction, so we need to make it negative. Okay, and T, I don't care about here. So again, I want to find S. So which formula does not include T? Again, V squared is U squared plus 2AS. So then 0 squared is 21 squared. Add 2 lots of minus 9.8 lots of S. I'm going to call, I'll call X. Just because I don't want my S to be confused with a 5. Okay. So then if I simplify this, I get 0 is, well, 21 squared is 441. Minus, well, 2 times minus 9.8 is minus 19.6. So if I add 19.6x, I get equal to 441. So x is 441 divided by 19.6, and that would be 22.5 meters. Okay, so that's saying the distance from when I started at the point X to this height, to the greatest height it reaches, the height is 22.5. Okay. So it's asking for the greatest height above the ground. So that is not just 22.5. That's 22.5 meters above from the point X. But X itself is 7 meters above the ground, right? So the ground. So overall, the height is these two added together, 22.5 and the 7 meters, right? So if I do 22.5, so the greatest height is the 22.5, add the 7, which will get me 29.5. Okay, so that is the greatest height above the ground. Okay, right. Okay, part B. Then it says the time of flight of the ball. Okay. So the time of flight means how long is it in the air until when it hits the ground, okay? Okay, then, so to work out this time of flight, so the time it's in the air, so again, if we start at this point X, then obviously it comes to the height, to the maximum height here, then obviously at the same height, it's then going to come back down to hit the floor, okay? So we want the time of this whole journey here. So, well, think about it. Ultimately, if we want the time of flight in the air, so it starts at X and then it ends and hits the floor back here, right? So it goes up and then comes down. Well, actually, what we can just do is consider that, well, the displacement, right? Firstly, the distance. If we consider from the point X initially, right? So it's 7 meters above ground, to then when it hits the ground. Well, overall, it's gone down. gone down by 7 meters. So the displacement will be -7, right? So I can start to do my C of that. So S will be -7 when it hits the ground because it's 7 meters below the point X. U, again, the initial velocity is 21. V, I don't really care about. So again, the speed. So again, when it hits the point on the ground, what speed would it be? I don't really care about that. Okay, and the acceleration. Well, the acceleration again is -9.8 because it's gravity. It's working downwards in the negative direction. And T is what I want to work out. Okay, so which formula does not include V? Well, it's this one. S is ut at a half at squared, right? Okay, and so if I sub my numbers in, -7, it's going to be 21t at a half, lots of -9.8t squared, right? So if I simplify it, I get -7 is 21t. Then a half of -9.8 is -4.9 t squared, right? And so you can see we get a quadratic in t. So if I add the right side to the left, if I add 4.9t, I'll get 4.9t squared, and -21t minus 7 equals 0. Then I can solve this quadratic. So if I do put it in the formula, so 21 plus or minus the root of -21 all squared minus 4 lots of 4.9 minus 7 over all over 2 lots of 4.9. So just put it in the quadratic formula to get the values of t. T is 4.597 to 3 decimal places, or minus 0.311 to 3 decimal places. Obviously, we know which one we're going to accept because this is negative. It doesn't make sense for t to be negative. The t is positive because it's time. So that means we can only accept t is 4.597 seconds to 3 decimal places. So that is the time it's in the air. Okay, that's the whole time it's in the air when it starts at x and then it comes all the way up and then all the way back down to then it hits the ground at this point here. That whole time is 4.59 seconds, right? Okay. So, okay, we've got this question here. And again, now a particle is projected upwards again from a point O with speed u. The greatest height reached is 62.5. So it's kind of in reverse, this one. Now we're told the greatest height, we need to kind of work backwards to kind of find the speed. Okay, so again, if I draw my situation, so it's projected from a point O. So again, if I call, I don't know, the O there. I'm not told anything about a floor, so I assume it just starts at O. Okay, so I have a particle, some little ball, right? And it moves up. I'm told it's projected upwards. So again, just basically kind of kicked or pulled up, essentially. So it moves up with speed u. So I'll say u speed, u meters per second. Until this maximum height, right? So the maximum height it reaches in the air. Okay, what's the height going to be? Okay. Oh, I'm told it's 62.5 meters above O. So I'm actually told it, yes. Okay. So it wants me to find u. And again, always when we're dealing with moving in the air, so moving up or down in the air, there's acceleration, there's a gravity acceleration downwards by 9.8, right? So that's the acceleration. So again, okay, so we want the initial speed u. So again, my s, well, the displacement, so we moved up by 62.5, so that's just 62.5. The initial speed moving up is just u. That's what we want to find. U is u. V is I do know the speed, right? It has to come to 0, right? So when it reaches the maximum height, it doesn't move any further upwards. It comes to 0 speed. A, the acceleration when it's moving down in the negative direction, going down, so that's negative 9.8. And T, I don't care about. So which formula doesn't have T in? Well, it's V squared is U squared at 2AS. So therefore, well, V squared is 0 squared is U squared at 2 lots of 62.5 times minus 9.8. And then if we simplify, we get 0 is U squared. And then if we do 2 times 62.5 minus 9.8, I get minus 1225. So therefore, U squared is positive 1225. So if we root that, I get 35, and there we are. Cool. So I can add that on. So that's my starting speed, 35. Cool. Then it says in part B, the total time for which the particle is 50 meters or more above O. So obviously we know the maximum height. The maximum height is 62.5 meters. But it wants it specifically the time when it's 50 meters or more above O. So if I sort of create another level here, and now let's say that's 50 meters. So I want the particle to be here. Obviously it's going to move up, and then it's going to come down at the same level, okay? So it wants this whole time where the particle, right, is 50 meters above this level O. So obviously it's going to start moving up to then its greatest speed, to then its greatest height of 62.5. Then it's going to come back down, and then it will reach 50 meters again, the 50 meter level, okay? So okay. So what's the time? So if we again if we do our Suva, well, if we're starting from this point O, well, we want it to be 50 meters above O, so the displacement has to be 50, right? And our initial speed, again, if we're starting from O, we now worked out the initial speed is 35. V, I don't care about, I don't think. A, again, the acceleration, it's negative 9.8. And T is what I want to work out, right? So again, I'm going to use, which one does not have V in? This one here, right? UT at a half AT squared. Okay, so then 50 for S has to equal 35 lots of T, add a half lots of minus 9.8 lots of T squared. Okay, so then if I simplify, I get 50 is 35T, and then minus 4.9 the T squared. So I get a quadratic, so I get 4.9T squared minus 35T, add 50 equal to 0. If I solve that, so T is 35 plus or minus the root of minus 35 all squared, take away 4, lots of 4.9, lots of 50, all over 2 lots of 4.9, and so I get T to be 5.169 to 3 decimal places, or T is 1.974 to 3 decimal places. So these two values make sense, both positive, right? They both seem sensible numbers. So yeah, those are my two times. So again, so what that means is it first reaches 50 meters above O, right? At time at 1.97 seconds. And then it reaches a maximum height here, then it comes back down, it returns back down at the same level, then at time 5.169 5.17 seconds, right? So that's the idea. That's what's going on there. So those are my 2 times. Cool. And so the total time then, well, the total time it's above O. Well, the total time basically it's above 50 meters. Well, it's the time in between these 2 times, right? So it starts above 50 at 1.97 seconds. Then it ends and comes back down at 5.17 seconds. So the time it's above 50 is just between these 2 times, right? So if I subtract them, so time above 50 meters, that's going to be 5.169 take away 1.974. And so if we work that out, that'll be 3.2 seconds to 1 decimal place. Okay, so that's the total time. It's strictly above 50 meters. Okay, so there we are. Okay, so hopefully you understand the main idea there, where it reaches maximum height. Then obviously the velocity it comes to 0 speed, and then it moves back down. Okay, but there we are. Okay, so I've got this last question here. So it's a bit more complicated because now we've got 2 balls to consider. Right. Anyway, so a ball A falls vertically from rest from the top of a tower 63 meters high. At the same time as A begins to fall, another ball B is projected vertically upwards from the bottom of the tower with speed 21. The balls collide from the distance where the balls collide. Okay, so let's just do it bit by bit. Let's focus on ball A first. So, we're told that ball A falls vertically from rest. That the rest means it's going to be 0 speed. From the top of a tower. So that's the key bit. So we have a tower, right? We have a tower, right? And then we have the floor. So this is the tower. And we're told it's 63 meters high. So 63 meters above ground, right? Okay, so we have the ball A, right? That's on top of the tower. So here, at this level, I'll call that A. And I'm told it starts from rest, right? So it starts with 0 speed, but it's going to move down, right? At the same time then, I have a ball B, which is now at the bottom of the tower, right? So it's at the bottom here, B. And I'm told that it moves up, right? It's moved up, it's projected up with speed 21. So it's going to move up at speed 21, right? So, obviously they're going to collide then, right? A and B. If one's moving down, one's moving up, they are going to meet somewhere in the middle, right? So, we're told the balls collide. So it wants the distance at the point where the balls collide from the bottom of the tower. So what's going to happen is, eventually, that A is going to move down, B is going to move up, and so eventually, at some point, they're basically going to be pretty much touching each other. So we're going to have A here and B here, right? So what we want to find is the distance from the point where the balls collide. So this point here, where they both meet, they collide, the distance where they collide from the bottom of the tower. So they want this height here. Okay, and as always, there's going to be acceleration, gravity. So it's going to be downwards by 9.8 because stuff is moving down and up through the air. Okay, so how can we deal with this and what can we do here? Well, what we can do is just consider them separately, right? So let's start with A. Let's do suvat with A, right? So for A, suvat. Well, if I just call this height from the floor, from the ground to when they meet, if I call that H, right, just height H, that's what I want to find. Well, actually, if I get rid of this, just move it somewhere else. So gravity there. what I can instead, obviously that's from the floor to the point they meet, but what about from the top to when they meet, this height here? Well, the overall height, again, the overall is 63. So if the first part of the height is h, then it's going to be 63 take away h, right? If overall, it's going to be 63 meters. Hopefully you're with me there. So if I do the whole 63 take away h, I then get this height left, if that makes any sense, right? Which means A would have to travel 63 take away h distance down, right? So it's moving down by 63 take away h. So I'll say that, okay? Right. Then, again, the initial speed of A is 0, right? It was at rest. V, I don't think I care about the final velocity when they meet here. I don't think I care about that. A, again, it's going down, but because A is going down anyway, we're kind of treating downwards as positive here. So generally, the direction we take to be the positive, so the direction we want to go in, is where it moves, okay? So if it's moving down, then that means the acceleration will also match that to be positive 9.8, okay? And then time, well, actually, if you think about it, if they both start moving at the same time and then they meet at the same time, the time is the same. If I just call that time t, then both their motions are in the same time, right? So I'm going to leave it there. So that means then, if I call that time t, and again, I don't care about v, which formula does not have v in, it's going to be this one here, right? S is ut plus a half at squared. Well, S is 63 take away h. And that's going to be 0 t, so 0, add a half, lots of 9.8, lots of t squared. So if I simplify that, I'll get 63 take away h is 4.9 t squared. Okay, I could perhaps rearrange this for h. So then h could be 63 take away 4.9 t squared, right? Obviously, I can't find h because I need to find the time during the journey, right? That when they move up and down. Then again, that's particle A, right? That's particle A. Now let's do let's do ball B. So now B is opposite. It's going to move up. So it starts here at the ground, and it moves up with 21 speed. Again, so we're considering the point from when they start. So it starts on the ground to when they meet. Well, the height, the displacement, right, the distance it travelled up to that point, it's just h, right? We said the distance from the ground to when they collide, they meet, is h. So that's my displacement. So S is h now. U, again, the initial speed upwards, it's moving up by 21 speed. So 21 for U. V, I don't care about. A, well, now it's because it's moving up, right? Upwards is the positive direction, so the acceleration downwards then has to be negative, right? Make sure you are very comfortable with why we make things negatives if they move if things are in the opposite direction to where they should be, right? So we make it negative there. Then T, again, is just T. Now it's the same T, because again, if they both start at the same time and they collide at the same time, well, the motion takes the same time, right? So it's the same time throughout for both balls to move. So therefore, again, we can use the same formula because again we don't care about v. So S is ut at a half at squared. So now h is going to be 21t at a half of minus 9.8 t squared. So if we simplify, we get h to be 21t minus 4.9 t squared, okay? And so at this point, we've got simultaneous equations, okay? So we've got h here and h here. So if I restate this as the first equation, and then I have h is 63 take away 4.9 t squared in the second equation, right? So I need to solve these simultaneous equations now, okay? So h and t. Obviously, at the end of the day, we just want to find the height h, okay, the distance from the ground to when they collide, h. But we're going to need to solve the simultaneous equations. Right, how can we do that? Well, it's a quadratic simultaneous equation, so think about maybe substituting. So again, I have h in both of them, so I can basically sub one equation into the other. So I'm going to sub, say, the first equation into the second one. So if h is equal to 21 take away 4.9t squared, then that means h here in the second one's going to be 21t take away 4.9t squared has to equal 63 take away 4.9t squared, right? And so if I add 4.9t squared to both sides, I get 21t is just 63. Well, that's a lot nicer to solve now, right? So then simply t is 63 over 21, which is 3. Okay. So that's saying the time it takes from when they start moving up or down, depending on what it is, when they start moving to when they collide is 3 seconds. But we want the height, right? We want h. So h, well, we're going to sub t into either equation. Let's substitute it into, say, the second one, right? So h is going to be 63 take away 4.9t squared. Well, if t is 3, h is going to be 63 take away 4.9 of 3 squared. And so if we work that out, we get 18.9. And that is my distance. That is the distance from the ground to the point where they meet. Okay, so that's 18.9 meters there. And that is my answer. Okay, so we've got some exercise questions then. I think I'd make the point as well. Some of these questions can be quite tricky, especially for the first time. They can be very daunting, especially the last few questions we've seen. The thing with mechanics is, yes, the questions are hard, but the questions, once you get used to them and you practice them, the questions don't differ. So it's kind of like you get in what you get out. So if you spend the time practicing the questions and what I've done makes sense, you can do that yourself. The questions won't be much different. Okay, so once you nailed it, you should be okay with the exam or whatever. Okay, but hopefully they made sense. Quite tricky questions they are though. But let's have a look at these questions. Okay, so this question, we're told a particle is projected vertically upwards from a point O with speed u. 2 seconds later, it's still moving upwards. Again, let's kind of draw what's going on. So again, we start from this point O, so the level O, and again we have a particle that's moving up. Initially, it's moving up with speed u, and then we're told that 2 seconds later, so let's say it's up here now. It's still moving up with speed a third u. Okay. Again, we're going to have acceleration, gravity going down, so 9.8 downwards. That's the acceleration. We need to find the value of u, firstly. I'm going to probably draw a floor as well. I don't need to, but I'm going to draw a ground level. So part A, we need to find the value of u. Okay, so we've got this situation here. So we know, so we're starting from this point here, which with initial speed u, and then we end up with the speed of third u. So s, I don't think I know anything about the distance, so I don't care about that. U is again u, the initial speed. V, the final speed at this point, is a third of u. A, deceleration, well, if it's moving upwards, which is positive, then downwards the acceleration has to be negative, so it's negative 9.8. And t is, well, we're given the time, it's 2 seconds, right? 2 seconds later. So 2 seconds. So which formula does not involve s? Well, it's this one here. V is u plus at, right? So then a third u is going to equal u, add or minus 9.8 lots of 2. So if we simplify that, we get a third u equals u, take away 19.6. So then if we solve for u, if we subtract u to both sides, we get minus 2/3. U is equal to minus 19.6. So if we divide minus 19.6 by minus 2/3, we get u to be 29.4. And there we are. Okay, so we can add that on to our diagram. So now 29.4 here. If I need to work that out, I can, but I'm going to leave that there for now. But there we are. That's the value of u. Then it says for part B to find the time from the instant the particle leaves O. So again, this point here, when it moves up from O, to the instant that it returns to O. Okay, so again, it's going to move up. Right, it's moving up, but then eventually it will move up no more, and then it will come back down. Okay, and then we want to find the time when it comes back down. Okay, so if we consider that, what time does it return back to O? Okay, the level O. Okay, so what's the time? So again, if it returns to O, so if we start at O and then we end at O, well, the displacement wise meaning how far overall from the start to the end have we gone away from O? Well, if we start at O and end at O, we've not moved anywhere at all, really. So there's no displacement. So what we can say is that S is going to be 0. U, well, again, the initial velocity, the initial speed is 29.4. We worked that out. V, I don't care about. So V now would be the speed when it returns back to O there. So I don't care about that. A, again, because if we're moving up, then acceleration would be negative, so minus 9.8. And T is what I want to work out. So which formula does not involve V? Well, it's going to be S is ut. S is ut at a half AT squared. So 0 is going to equal 29.4 lots of T, add a half lots of minus 9.8 T squared. So again, if you simplify, we get 29.4 T minus 4.9 T squared. So then we can solve this, we can just factorize it. So then we get T lots of minus 4.9 T, add 29.4 is set to 0. So that means T 0 or minus 4.9 T, add 29.4 is 0. So we set both brackets to 0. If we solve this one, well then 4.9 T is going to be 29.4. So therefore T is 29.4 over 4.9, which would be 6. Okay, 6. So that has to be the time then, right? So again, so initially it starts at time is 0, right? So it starts at the point O at time is 0. Then it returns all the way back down to O at time is 6. Okay, so that is the time. Okay, 6 seconds there when it returns back to the point O. Okay. Okay, so we're going to look at some exam questions now. And they do, I will say they do love asking questions about this, about falling and suvat and stuff like that. So here we're told a small stone is projected vertically upwards with speed 39.2 from a point O again. Okay, so we have a point O and initially, okay, so it's going upwards with speed 39.2. Okay, the stone is modelled as a particle moving freely under gravity from when it's projected until it hits the ground 10 seconds later. Okay, so what that's saying is So the only thing really we care about here is that it hits the ground 10 seconds later. So again, it starts from this level O, and then the ground level somewhere down here. Then we're saying 10 seconds later, so then it reaches a maximum point. Then after that maximum point, it comes back down, and then it hits the ground 10 seconds later. Okay, so the time is 10 between when it starts to when it hits the ground. Okay, so it wants to find the height of O above the ground. So again, O is above ground. We don't know the height though. That's what we want to work out. Right, and again, as always, there'll be acceleration acting down because of gravity, which is 9.8 meters per second. Okay, so right. So we want to find the height firstly. So the distance above the ground level. Okay, so ground here. Okay, so let's use that. So again, we're going to start. So okay, if we start from, well, that's S. So we start from this level O, and we end on the ground level here. Hits the ground. Well, the height is the displacement, right? But because we're moving upwards, right? We're starting by moving up. We're treating positive upwards as positive. The thing is, the distance is moving down to the ground, so it has to be a negative distance. Okay, so remember that the displacement is we're going down by h overall, so we're going down by the height, so it's negative height, if you will. Okay, if that makes any sense. So negative h, because it's going down, we're going down by the height, so negative h. U is the initial speed, which is 39.2. V is, I don't think we care about V at this point. The acceleration, again, it's going down. If we're going up here, downwards is negative, so negative 9.8. And T is, well, we're given the time, 10 seconds, right? So which formula does it include V? Well, you'd find, again, it's S is ut at a half at squared. So then minus h. It's going to be 39.2 lots of 10, add a half, lots of minus 9.8 lots of 10 squared. So then you'd get minus h, if we work all that out, just put that in the calculator. We get negative 98. Now that's reassuring, because obviously we get a negative, we can just cancel the negative out. To get positive h is 98, so the physical distance is positive here, so that's 98. Cool. So now we can say that the height above the ground is 98 meters. Right, then it says for part B, find the total length of time for which the speed of the stone is less than or equal to 24.5 meters. Right. So, okay, interesting question. So we want the time, so when the stone has a speed of 24.5 or less. Now, think about it, we're starting with a speed of 39. Well, 24 is less than that, right? So the idea is, because the gravity is slowing it down as it moves up, right? When it moves up, it goes slower and slower, to then it goes to 0, then it comes back down. We want basically, I guess, the point. So this particle, so when it goes up, right, the instant it goes to 24.5 meters speed, and also then when it comes back down, because then it's going to go up to, it's going to move up, and then it's going to come back down, and then when it comes back down with speed 24.5 as well. Okay. So we want. So what we essentially want to consider is this point is this situation where the ball, the particle, the stone, when it reaches a point where the speed is slowed down to 24.5 from when it starts at 39. Okay, so it goes up by 24.5, then comes down by 24.5 as well. So what times do that happen? Okay, so again, let's consider that. So S, well, we don't know this particular distance. We don't know the height when it reaches 24.5. We don't really care about it. Okay, so well, again, if we treat the initial speed as 39.2 up, so it's 39.2. V is what I do care about, the speed when in particular, when the speed is 24.5, right? Because we want to find the time when it reaches these speeds. Okay, so the speed of 24.5. A, again, if we're going upwards, then acceleration going down has to be negative, so negative 9.8, and T is what we want to work out. So the formula that excludes S, that's going to be V is U plus AT. So then 24.5 is going to be 39.2 minus 9.8 lots of T. So then we solve this for T, so minus 9.8 T. Well, if we do 24.5, take away 39.2, we get minus 14.7. Therefore, T, if you do 49.7 divided by 9.8, minus, divide that. So minus 49.7 over minus 9.8, we get 3 over 2, or 1.5. Okay. So, 1.5, that is this time here. So time is 1.5 when it first goes up by 24.5. Right? Now this is where the really tricky idea comes in. Obviously that's the time when that's the time when it first reaches 24.5. But then obviously it'll go to 0 and then it'll come back down. Okay? And it comes back down and then it will reach the same speed again. Now, we need to work out the time it reaches back to 24.5. Now, to do that, we'll actually consider again, this velocity is now downwards. So essentially, the thing what we need to change now is we look at our suvat. Originally, we said it's positive 24.5. If it's going downwards now at this time here, it has to be negative 24.5, right? So if we do the exact same thing now, nothing else has changed other than the speed, the velocity, the final velocity. If we're going up, right, then down has to be negative 24.5 speed, and A again is minus 9.8, and T is still what we want to work out. So if we then do the exact same formula, so V is U plus AT, you're going to get minus 24.5 is going to be 39.2 minus 9.8 of T. And so then you're going to get minus, so then if you do minus 24.5 minus 39.2, you're going to get minus 63.7. It's going to equal minus 9.8 T. So therefore T is minus 63.7 divided by minus 9.8, and that will get me 6.5. Okay. Which is great. I get a positive time, which makes sense. So this time is now 6.5. Okay. So hopefully that makes sense with what's going on. Okay. Again, quite a tricky scenario, that question. So it first reaches up. It goes up. It reaches a speed of 24.5, 1.5 seconds after the start. Then it comes back down after all that, and it returns back to 24.5 speed 6.5 seconds after the start. Okay, now that's not the question, right? It wants the total length of time when the speed is less than or equal to 24.5. So in other words, it wants the whole time between it starts here and ends here. Well, actually, because we worked out the two end times, we can just take them away to get the time in between. So the time in between equals 6.5 take away 1.5. That's going to be 5 seconds. And there we are. Okay, there we are. And then part C, state one refinement that could be made to the model to make your answer to part A more accurate. So in other words, what more accurate in terms of real life, so make it more realistic. Now there are two sort of stock answers you can kind of say for this, because it does come up. So the two things you can say, well, first of all, as if you remember when we looked at modelling assumptions, we looked at a particle being negligible. We ignore essentially air resistance and also rotational forces. Okay, now you can use either. Air resistance might be probably the more common one, because the whole idea is we're moving through air, right? Like a skydiver, right? If you're going to go down, a skydiver is going to get a lot of air resistance as it moves through the air. If we're ignoring air resistance, we're ignoring probably quite a significant factor, right? As it moves down and up through the air. So the refinement could be to incorporate air resistance, right? To make it more realistic or accurate, right? So the model could include air resistance to make it more accurate, because in reality, obviously, if you move down and up through the air, you're going to get air resistance. The other stock answer is sometimes I might say other than air resistance. The other answer could be is when we used G here. So G, remember, we said is 9.8. That's the acceleration going down because of gravity. In reality, we saw that G is actually quite a large number. It's like 9. It's like not a large number. It's like a large decimal. So it's like 9.8. Blah 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 blah. So in reality, we just shortened the answer to 9.8. Okay. That means that answer isn't going to be as accurate as it can be, because there's a rounding sort of error, right? There's a rounding thing going on, which makes the answer less accurate, right? So the other answer is use G, or use G to more decimal places, okay? Because obviously we use it to one decimal place here, but actually there are loads of decimal places. So you could make the answer a bit more accurate by just making G not rounded, okay? And so there we are, okay? Let's have a look at this question here. So here we are told at time t0, a small stone is thrown vertically upwards with speed 14.7 from a point A, and then time capital T seconds, the stone passes through A backwards. Okay, moving downwards, sorry. Okay, so let's again sort of sketch, depict what's going on. So we're at a point A here. So initially it's at the point A, and it's thrown upwards. And again, the speed is 14.7 upwards. Then, after t seconds, the stone passes through A again. So the level A, so if we extend the level A in that way, right, it will return back to the height of A. It will return back to A, moving downwards. I don't know what the speed is. We're not given the speed at that point, but I'll just say that. And again, acceleration downwards is always going to be 9.8. So that's the idea. So we start at the point A with this initial speed, and then we return back to A. I'm not given the speed there, but that's all I'm given. I'm also given the time as t, and I need to find t firstly, right? Okay. So if I do see that then, well, S, well, if I started at the point A and end at the point A, displacement wise, I've not gone anywhere away from A from the start to the end, right? So there's no displacement or overall sort of distance travelled, right? So specifically how far away from A I am from the start to the end. because I'm at the same point essentially. Anyway, so S is 0. U, my initial speed is 14.7. V, I don't care about because I'm interested in time. A, well, if we're going up, right, up is positive, then the acceleration down is negative. So negative 9.8, and T is capital T. And so I need the formula that excludes V, and again that's going to be S is ut at a half at squared. So if I sub these in, 0 is going to be 14.7 big T at a half of minus 9.8 big T squared. So if I simplify, I get 14.7 T minus 4.9 T is equal, T squared, sorry, equal to 0. If I factorise, I get T of 14.7 take away 4.9 T set to 0. So that means T is 0, or 14.7 take away 4.9 T is equal to 0. So 4.9 T is 14.7. So therefore T is 14.7 divided by 4.9. And that will get me 3. Okay, just 3. So there we are. So obviously it makes sense. It makes sense to accept this value of T and not 0, because obviously we start at time 0. So the time after when it returns back to the point is 3 seconds. Okay. Right. Then it says find the total distance travelled by the stone in the first 4 seconds of motion. Right, so what we worked out here is, what we can't do, we can't just say, well, T is 4. If we use Suvat, we can't just use T as 4, because we asked for distance, okay? What's going to happen is, because we said that the time is 3 seconds, so the time when it starts at A, it moves up, and then obviously it reaches some speed of 0, right? It comes to a maximum height of 0. And then obviously once, then it's going to come back down. Again, it's going to start at 0, and then it's going to come back down. We said this whole time, when it starts at A, goes up. So it goes up, then comes back down, right? That whole time is 3 seconds. So if we were to, and then 4 seconds, maybe it would be down here somewhere, right? If we just skipped right to this initial point, to this point here, 4 seconds after, we'd be missing out all the distance when it travelled up to then this point 0 speed, right? We'd be missing all that height the particle travelled up, and all the distance the particle travelled down up to that same point, okay? We need distance. Distance, it does not matter what direction we go in. We just care about physically how far we travelled. It's not displacement. Displacement essentially only cares about how far we travelled, particularly from the starting point to the end point, okay? It doesn't account for the fact you might have travelled distance in between, okay? It doesn't account for that. We need to account for that here. So we basically need to consider 2 different journeys, okay? We need to consider the journey, firstly, when it starts at 14.7 upwards, and then it stops moving up. So 0 speed here. That'll get me this distance here. And then we're going to consider the journey from 0 to this, when it reaches some point here, after 4 seconds. Anyway, let's consider this part here, okay? So I'm going to label first part of journey. So when it reaches the maximum height, right? So S is what I want to work out, the distance. U, again, initially at the start, I'm starting with 14.7 speed. V is going to go to 0 if it reaches maximum height, right? It doesn't go up anymore, so it has to go to 0 speed. Acceleration, again, if we're going upwards, then acceleration downwards is minus 9.8. And t is, well, we don't care about t. Okay. So the formula that does not include t is v squared is u squared at 2as. So therefore 0 is going to be 14.7 squared. Add two lots of s, I'm going to call x, okay? X of minus 9.8. So then if I simplify, I get 0 equals 14.7 squared is 216.09 minus 19.6x. So if I solve for x, well, x is going to be 216.09 divided by 19.6. And so that will get me 11.025 meters. And so there we are. So that is telling me the distance from when we start, the distance from when we start to this maximum point in the air where it doesn't move anymore. So this distance is 11.025 meters. Okay. Right, so now we want this distance here, right? This whole distance from when it goes back down. So again, it starts from 0 and then it comes all the way back down to this point here. And we're told that the whole journey from when it starts originally upwards, it starts from A going up to then this end point here, the whole time is 4 seconds, right? Now, the thing is, they're giving us the time for a reason. We're going to need to use it. I think the easiest way to proceed is consider splitting this time up. So again, the time here, so the time from when it starts here and ends here, right? So that's again the time for the first part of the journey, right? So this time here, we can use that we can use SUVAT again, right? So again, for the first part of the journey, I now want the time of the first part of the journey. So again, the distance travelled, well, we worked that out, it's 11.025. U, again, we start with 14.7 speed, and then it ends at 0. The acceleration is minus 9.8, and T is what we want to work out. Okay, well, again, you can choose whatever formula you want, really, because we've got all the values we need. Well, I'm just going to avoid S. Maybe in an exam situation, you might be wary about maybe that value might be wrong, so it's best to pick the values that you're given, right? So we're going to use V is U plus AT because that's the formula that excludes S. So therefore 0 is going to be 14.7, take away 9.8 lots of T. So therefore 9.8 T is 14.7. So T is 14.7 over 9.8. And that will get me 1.5. Okay, quite nice. So that's saying the first part of the journey that I'm saying, from when it starts and then it ends by not moving, that time is 1.5. That means the whole second, the other part of the journey, but from when it starts so the first part is when it goes up. The second part is when it's going to come down all the way to this end point here after 4 seconds overall. So if overall it's 4 seconds and the first part was 1.5 seconds, the second part here, the second part is going to have to be 2.5 seconds, right? So now we can use that. So if we then start at this point here with 0 speed and then we end here, obviously we don't know the speed, but we don't really care. We can work out this distance here. Okay. So if I then now consider the second part of the journey, when it comes down, again, we're going to, the distance is what we care about. We know it has to start with 0 speed. If it starts from coming down, it starts from rest. V, I don't care about the final speed. A again. Now, if we're going down, because now we're considering it going down, acceleration is now positive because it's gravity, right? It's going down. So positive 9.8, and t, as we discussed, has to be 2.5 seconds. So now the formula that excludes v is going to be s is ut and a half at squared. So s then I'm going to call y. Now I used x last time. I just don't like using s. You can use s. It'll look like a 5. I know it will. So then y for my distance is going to be 0 and a half of 9.8 of 2.5 squared. So very simply, the second distance, if we work that out, that is 30.625 meters. So that whole second part, the whole distance of the second part when it falls down is 30.625 meters. Okay. Right, so now we can work out the total distance travelled in the whole 4 seconds. So the whole journey, the first part of the journey when it goes up, then the second part when it comes down, right? Well, we're going to add these two numbers together, right? That'll give me the total distance. So total distance in 4 seconds. That's going to be 11.025. Add 30.625 to get me 41.65 meters. And there we are. Okay. Then it says in part C, state one refinement that could be made to the model apart from air resistance. Oh, okay, so they took that away from us. Well, the other one, as I discussed last time, to make it more realistic, you can again use a more accurate answer for G, so the acceleration of 9.8. So use a more accurate value of G, which is the acceleration due to gravity. So use more decimal places or something like that, right? And there we are. Okay, so we've got this final exam question here. It's quite loaded. So here we are told at time t0, a small ball is projected upwards, so it's going up with speed u from a point A that's 16.8 meters above ground. Okay, so what I'm going to do is just again just sketch the scenario. I'm not going to read it all out. Okay, so what we've got, so we've got a ground level, right? We've got a ground. We're told it hits the ground, so there's a ground level. We're at a point A initially, that's 16.8 meters above the ground. So let's say A is here, which is 16.8 meters up. And initially we have this ball with speed u. Okay. And the speed of the ball, the instant immediately before it hits the ground, for the first time is 19. Okay, so we're talking about when it hits the ground. Well, if it's going up with this speed, up by u speed, it's obviously going to go up and keep going up to when it hits 0 speed, right? And then it's going to come back down the other way. It's going to go down to 0 again, and then it's going to come all the way down and then hits the ground. This speed when it hits the ground, we're told, is 19. Okay. And as always, there's going to be an acceleration downwards. Now, I did pay attention to this. I saw it. The acceleration due to gravity, which is g, the acceleration downwards, we're told has to be 10 here. Okay, we can't use 9.8. You must pay attention. Okay, they round 9.8 to 10. Okay, so we need to use 10 for g for the acceleration, not 9.8. Sometimes they do say that, so you do need to be careful with what value they ask for, okay? If they don't specify, you need to use 9.8, okay? But if they do specify it's 10, you need to use 10 here, okay? Right, is there any more information we're given? We're told the ball hits the ground for the first time at time t seconds, so I guess I'll call that time t. The motion of the ball from the instant it's projected until the instant due to gravity, blah blah blah. Okay, we need to use the model to show that u firstly is 5. So this u here, the initial speed. Well, so if we look at our information, well, we start with speed u. We also know the end speed all the way down here, right? So what we can do, well, simply the displacement. Well, if it's 16.8 meters above the ground, we start from, right? Overall, if we start here and end here, the overall displacement, we've gone down by 16.8 meters. So it's negative 16.8, right? That's the displacement. We've gone down by that distance overall. Right. U, again, it's going up by speed u, so just u. V, I'm told, is 19, but the speed is going downwards. At this point, we're going down, so it's negative 19, right? A, deceleration, again, it's negative 10 because it's going down. And T, we don't care about at this point. We need to find U, okay? So, what formula excludes V? T, sorry, it'd be V squared is U squared at 2AS, right? So if we sub that in, we get minus 19 all squared is going to be u squared, add 2 lots of minus 10 of minus 16.8. So that would be 361 equals u squared, add 336. So if we take that away, we get u squared is 361 take away 366, which is 25. So therefore u is just 5. And there we are. We've shown that u is 5 there. Cool. Then for B, then it says to find the value of t. So now we want the time during this whole thing, right? So now we're going to do the same thing, the same suvat, but now we want to find time instead. So again, from when we start with speed u and the end at this speed here, the overall time, so the displacement, we've gone down by 16.8. So negative 16.8. U, well, we know what u is now, it's 5. V, we also know what v is. Again, it's going to be negative 19. We know that the acceleration is minus 10. And t is what we want to work out. Well, let's exclude s, right? Let's exclude s, because now we can use v is u plus at. Again, you can use, because we've got all the values here. You can just pick any equation you want at that point. I just prefer to exclude s. I guess this formula is nicer, but anyway, absolutely does not matter what you use. I'm going to stick with this. So now I can say that minus 19 is going to be 5. Minus 10 lots of t, okay? So therefore, if I subtract 5, I get minus 24 is minus 10t. Therefore, t is minus 24 over minus 10, which is 2.4. And so there we are. That is 2.4 seconds there. Okay. Then it says for part C, find the time from the instant the ball is projected until the instant when the ball is 1.2 meters below A. So now they've specified we want to end up 1.2 meters below. So if I now sort of add that onto my diagram, well, A is 16.8 meters above the ground. So if we want to be 1.2 meters below A, so that's going to look something like this, right? Something like that, right? If this is going to be 1.2 meters below A, then Yeah, I guess I'll just leave it there. You could work out this distance as well. If you know the total distance underneath A has to be 16.8, then you can just take that away from 1.2 to get that distance. I don't think we need to do that. But what they want from me is the time. So the time when the ball is projected, so at the very start, again from the very start with this speed u. I know u is 5 now, so I can add that on. 5. To now this point, not at the point where it hits the ground, but when the point it's just 1.2 meters below A, right? Right, so again, if we start at this point here, so start where the speed is 5 up, if we use Suvat then to kind of work this out, so part C, S, well, if we want to start at this point A and we want to end at a point that's 1.2 meters below A, well, we've gone down by 1.2 meters, so it'd be negative 1.2, right? Overall, the displacement overall. Again, U is 5. V, I don't know, and I don't care about it. A, again, it's going to be negative 10, and T is what I do want to work out the time. Okay, so if I work that out, then what formula does not include V? Well, it's going to be S is UT at a half AT squared. So therefore, minus 1.2 is going to be 5T at a half, lots of minus 10T squared. If I work that out, I get minus 1.2. If I simplify, I get 5T minus 5T squared. Okay, so then if I move everything to one side, I get 5T squared minus 5T minus 1.2 equals 0. This is now quadratic, so if I solve this, I get T is 5 plus or minus the root of minus 5 all squared minus 4 lots of 5 lots of minus 1.2 all over 2 lots of 5, and that will get me T is 1.2, or T is negative 0.2. Okay, well that's fairly straightforward. We can't have negative time, so T is positive, hence we can only take the positive solution of 1.2 seconds. Okay, and that is my answer. Okay, so then it comes down 1.2 meters below A at time 1.2 seconds. Right, so there we are. Cool. Then in part D, it wants me to sketch a velocity time graph for the motion from 0 to capital T. Capital T was what was it? It was 2.4 seconds, right? That was capital T. That's what we worked out in part B. That's 2.4 seconds, sorry. So between 0 and 2.4 seconds, right? Stating the coordinates at the start of the end point of the graph. Okay, so we need to sketch a graph for this situation. Right. Do it down here. So again, any velocity time graph has a velocity against time. So we're going to have velocity and then time here in seconds, and velocity in meters per second. So this is just thinking back to velocity time graphs. So let's have a look at the situation we've got. So let's just review what we're told. Okay, so we're told initially at time 0, a small ball is projected upwards with speed u from a point that's 16.8 meters above ground. Okay, we only care about the speed essentially, right? So the speed is 5. So we start with 5. Okay, that's all I care about really. So the velocity, we need to start at 5. Now think about it. At the end, right? At the end when t is t seconds at the end. So this is 2.4 seconds, right? At the end of the journey. The speed when it hits the ground at this end time is 19, right? So at the end, so then if we have what was t? 2.4 seconds, was it? What's capital part B? 2.4. Okay, there we are. I should call that capital T, actually. There we are. So we end at 2.4 seconds with a speed of 19. Now, either it's going to be 19 above, or you should know velocity can be negative, so we can extend to negative velocity. Okay? So actually, if I just move 5 down here, right, so then 19 is going to be either all the way up there, or 19 is going to be all the way, if I extend it, all the way like down here, right? So either 19 and positive 19 or negative 19, right? Because it's velocity. Velocity can be positive or negative, depending on the direction. Now, which one is it? Well, actually, it's this velocity here, right? It ends at 19. As we already saw, it's going down, which means it has to be negative velocity. We already saw that, right? We discussed previously that this velocity is negative, right? Because it's going down. So actually, our graph needs to end here at negative 19, okay? So essentially, we just get a line starting at 5 and ending at minus 19. Now it asks for the coordinates at the end point. So at this end, at the start, that's time is 0 and the velocity is 5. Then at this end point, the time is 2.4. The velocity is minus 19. Okay. Now, why is it just one straight line? Well, think about it. Think back to velocity graphs. We discussed that the acceleration is the gradient, right? But this whole time we've been using the acceleration to be negative 10. It's going down by 10. So the acceleration is always 10 the whole time. So the gradient has to always be minus 10. Okay, I can add that on if I want to. I could annotate that on. I don't need to, but the gradient I could say is minus 10 for this little line here. Okay, that represents the acceleration always being equal to minus 10. Again, because it's going down. Okay, and so there we are. So that's the velocity time graph. Okay, that's the idea. When it's falling down, this is what the graph should look like. Okay, just one line. Start with the start velocity and the end velocity there. And the gradient will always be minus 10. It's the same straight line, the same gradient all the way through. Okay, so that's my graph. Right. Okay, we're nearly there. We've just got these little weird one markers to deal with, right? So we're told now in a refinement of the model, the motion of the ball, the effect of air resistance on the ball is included, and this refined model is now used to find the value of u. So u is the starting speed again, right? So what effectively it's the same idea, it's the exact same stuff going on, but now we're including air resistance. Now you don't need to calculate air resistance or anything like that in this with the stuff we worked out, but you need to consider what effect it could have. Well, what effect would it have on you? So basically what's going on is we need to incorporate air resistance into the model. Now the only thing that's changing here, the only thing that needs to change with this model we're working with, the only thing that needs to change is u, the starting speed. Every other aspect has to remain sort of the same. So it needs to end, so it needs to still hit the it still needs to hit the ground with the speed 19, right? Now think about it. Okay, so if I still need to hit the ground at say 19 speed, I need to, if I'm going to add air resistance that slows me down, I'm going to need to change my starting speed, right? Now think about it. If the air resistance is going to oppose my motion, right, as I move through the air, if I still want to end at the same speed, and I've got something that's trying to slow me down, I need my starting speed to be even bigger to compensate for that, right? So my answer is u has to be bigger than 5, right? It has to be a bigger starting speed. So u, with air resistance, right? So with air resistance, u, the new value of u, right, when I include air resistance, has to be larger to oppose the air resistance that will slow the ball down. Which will slow the ball down, okay? So that's the idea. If I still want to end at the same speed, if I have some resistance that's going to slow me down, I need to make my starting speed even larger. If that makes any sense, okay? So that's the idea. So it has to be larger than 5, right? So there we are. Okay, then in part, that's part E, sorry. Part F then, the final part, suggests one further refinement over the air resistance, alright? So again, over the air resistance. The other one is, again, use a more accurate value of G. So to more decimal places, right? Because obviously they even said G was 10 here. That's not very rounded at all, right? We use 10. So actually they can round G to like 9.8 or something to make it more accurate. But that's the answer I can use to make the model more realistic, to give me a more realistic, precise answer. Okay, so that's it. That is vertical motion, that stuff moving up and down, and that's really the end of the chapter. So hopefully you're quite comfortable with using SUVAT now to work out various missing information to do with things moving, right? So the time, the displacement, the velocity, the acceleration, right? But that's it for now. I'll see you next time.